If your crystallite size comes out to be 2 nanometers or even 500 nanometers, there is a very high chance that something is wrong. In this video, I will walk you through the top 5 mistakes that students and researchers make when using the Scherrer equation, and more importantly, how to fix each one step by step. By the end of this video, you will be able to calculate crystallite size from XRD data accurately and with confidence. Let's begin with a quick recall of the Scherrer equation. Here, D represents the crystallite size, K is the shape factor, typically around 0.94, lambda is the X-ray wavelength. For copper K alpha, it is 1.5406 angstrom. Beta is the full width at half maximum in radians, and theta is the Bragg angle. Now keep this in mind. This equation assumes no lattice strain and works best when the crystallite size is below about 200 nanometers. Even a small mistake in any of these parameters can completely ruin your result. Then let's talk about the first and most common mistake, using FWHM in degrees instead of radians. Most XRD software gives peak width in degrees, but the Scherrer equation requires radians, so you must convert it using the standard formula. If you skip this step, your result can be off by nearly 57 times. Here is another very common mistake. XRD patterns are plotted in 2 theta, but the Scherrer equation uses theta, so what should you do? Simply divide the value by 2. If you directly plug in 2 theta, your calculation will be completely incorrect. Now consider this, the peak broadening you measure is not purely from your sample, it also includes instrumental effects. To correct this, use a standard sample, such as silicon, to determine instrumental broadening, then apply the correction formula. If you ignore this step, you will underestimate the crystallite size. Another common mistake is extracting FWHM manually from noisy peaks without proper fitting. This leads to incorrect FWHM and ultimately wrong crystallite size. Instead, always use proper peak fitting tools such as Origin Pro. Apply fitting functions like Gaussian, Lorentzian, and most importantly, Voigt. Voigt fitting is generally preferred for XRD peaks as it provides more realistic results. So remember, the better your fitting, the more reliable your results will be. Now, a very important conceptual point. The Scherrer equation gives you crystallite size, not particle size. A single particle can contain multiple crystallites, so if you interpret it as particle size, you may draw incorrect conclusions. Let's clarify this further. XRD provides an average crystallite size, while TEM shows the real space structure of your material. In TEM, if your nanoparticles are single crystalline, then particle size is approximately equal to crystallite size. But if they are polycrystalline, then these two are not the same. To go deeper, use HRTEM to observe lattice fringes and identify different crystalline domains. So think of it this way, XRD tells you the average truth, while TEM shows you the local reality. Now, here are some important tips to remember. The Scherrer equation gives crystallite size, not particle size. A single particle may contain multiple crystallites. Before performing your calculation, always use a strong, well-isolated peak. Use the correct shape factor, typically around 0.94. Also consider strain effects using methods like the Williamson-Hall approach, and most importantly, never confuse crystallite size with particle size. If you found this video helpful, make sure to like and subscribe for more tutorials on XRD and material characterization. Thanks for watching, and I will see you in the next video.